So now we want to create a noisy data set. And by noisy data set, I mean a data set of two labels, clean audio and noisy audio. Because it's really common for some people to add different noise sounds to their audio, which kind of makes them not suitable for deep learning. Something like this ram bell sound, are randomly added to different portions of YouTube videos, audiobooks, etc. So our goal is to use a deep learning model to scan the whole large audio file and automatically detect where this type of noise happens in the audio. And for this, we will have to take a bunch of steps. Now, if most of you probably have come here from a deep learning background in computer vision or NLP, and in those two fields, when you do data pre-processing, you take some usual steps, and we're going to take those similar steps. The steps are similar in terms of normalizing audio files, making sure they are in a specific range, combining them, augmenting the data to create a balanced data set, etc. But in some sense, it is completely different because we're working in a completely different paradigm compared to computer vision, for example, where if you want to augment an image, you will probably rotate it, you will warp the image. In audio, when you want to augment it, you want to roll the audio or shift the audio a little bit, or you want to combine two different sounds together. So we'll see mathematically, but also in terms of code, how this concept works. So initially, I'm going to teach here resampling, padding to make sure noise is the same length as the original audio window size, and rolling the noise such that the noise will appear in different segments of the audio clip. So for that, we're gonna first import necessary libraries. This time I'm gonna import matplotlib, pyplot as PLT, just to plot some of the waveform. And the next step would be to have a look at the noise and manipulate it a bit. So for that, I'm gonna import Torch and import Torchaudio. So these are the necessary libraries we need here. Now, in my folder, current working directory, this is my noise file. It's an MP3 file. So I'm gonna set it as the noise file name. And I'm going to load it with Torch. So torch audio.load. We will need the file path. So noise file name. We will also need to pass frame offset and number of frames. My noise is probably around 1 second, so I don't need to take a sample of that, so I can load the whole noise all at once. Now, if you remember from before, this is gonna give us a noise wave as a torch sensor and a sampling rate for the noise. So we have the noise loaded. It's 48,000 sample rates. So we can manipulate it now. So you might want to get the sampling rate of your original audio. So my original audio is an audiobook, open source on LibriVox.org. I'm looking at Pride and Prejudice. You can try out different audiobooks as well. You click download on one of them. In this case, I downloaded Pride and Prejudice. And you can take a listen.
I recommend you, however, as a friend, not to give implicit confidence to all his assertions. For as
Okay, so it's a really long book. I probably will be fine with the 47-minute chapter over here. So I can just extract this long audio file. So this is my original audio. Now, if you want to create a noise detector, you will basically say, this is my clean audio, so clean file name, and I want to randomly add this noise, this bell noise, to different portions of this in real time and create a data set. Now, since I add the noise myself, I already know where the noise is, so I already know where the label is. So that's the smart trick, trying to create a synthetic noisy data set. You don't need to now manually label each portion of this audio, and that works really well across different domains. In computer vision, we can also manually add noise, so that's what stable diffusion is all about. Same thing with text. So in this case, I'm going to get the sampling rate of my MP3 file, which I downloaded from LibriVox. And for that, I would use Torchaudio, its info method. If you remember, it gives you a metadata of a given audio file. I'll pass in the clean audio file name, and it should give me a metadata object. Okay, we got the metadata. Now we can look at different attributes of this metadata, like number of frames. But what I'm interested in is right now sampling rate. So sampling rate of the audio is 24,000 samples per second. Now, at this stage, I can simply resample my noise to be the same sampling rate as my original MP3 file. Right now, we are downsampling from 48,000 to 24,000. For that, we can use Torchaudio functional. Similar to Torch, Torchaudio has this functional module where you can use different common audio functions. So resample is a common audio function which takes in a waveform, its own original frequency, in this case it is 48,000, and the new frequency to resample it to, in this case the clean audio, 24,000. And we can keep the rest as they are. So here I'll go say, if I want to do this operation, because it's an operation, it's going to be expensive in the long run, I'm going to say if the sampling rate of my clean audio is not the same as my sampling of noise, then do Torchaudio functional resample. So resample my noise wave. The original frequency would be 48,000 into 24,000. Of course, I want to keep the variable names to make sure it's modular. So SR into metadata SR. That's going to be my new noise wave. So let's take a listen to it before we resample and after. Let's see if we notice any difference. So just like before, I'm gonna from ipython.display import the audio module so I can display audio in Jupyter Notebook. Now, since we're downsampling from 48,000 to 24,000, we expect to see some degradation of audio quality. Of course, if it's high quality music and you're a musician with sensitive ears, it might be noticeable. But this simple noise, I don't think it's going to be noticeable. Let's verify this. So I want to display this noise wave, and I'll pass in the rate, sampling rate. And after I resample, we'll take another listen with the new sampling rate, which is 24,000. Before, after. So it sounds pretty identical. Now, for the next step, we can now combine any portion of the original audio file with the noise because they have the same sampling rate. So let's go a bit here and see, after you resample the noise, you have to pad it to the same length as your window size. Let's see how padding works in audio. In PyTorch, you have this really handy pad function. It is part of the original PyTorch neural network functional called pad. The documentation might seem confusing at first. It will take an input tensor and a pad as a tuple, which should be divisible by 2 or even. And you can pass the mode. We usually use constant to pad with a constant value, or you can use reflect, replicate, circular. These are mostly used for images. You want to reflect them or use the nearest value. And if you choose constant, you can pass the value to be padded into. You can look at the examples. Still, they might be a bit confusing. So let's first see how padding works for audio. So before I pad, I want to just first plot my audio. So PLT plot noise wave. Of course, before you plot it, you should check the shape because matplotlib would expect something that's one-dimensional. In this case, it's two-dimensional. So if you plot it, it's gonna interpret the first axis, which is the first channel, as the X, second axis as the Y. It's not gonna display what we want. We want the waveform. Basically, you should select one of the axes, one of the channels, and plot it. So this looks like silence and then noise sound, and kind of fades away at the end. So for a variety of reasons, you want to have both your noise file and also your original audiobook file to become mono. What does it mean? So instead of having two channels, you want to have one channel. What most people do is they take the average of both channels. So in this case, we want to take an average over the first dimension here and say noise wave mean over the first axis. And if you look at the shape, it will get rid of the first axis. You can take a listen to this. This is gonna sound identical to the stereo noise. So I'll just copy paste it here. This could be problematic, this approach, especially if you're doing a generative AI, you want to generate speech, music, audio. If you take the mean, what is going to happen is that it's going to take for each sample the value of the left and right channel and average them together. In spoken audio, this could be common that the two channels, when they were recorded or when they were saved on a computer, are not completely synced. It might not be noticeable to human ear, but there might be some millisecond missynchronization lag between the two channels. The problem this is going to cause, if you merge them together and feed them to a generative neural network, it's going to generate audio that's more prone to hallucination. So to avoid all of these potential future headaches, we'll initially pick only one channel, either left or right is up to you, as our audio, both for the noise and the audio book. So I'll come back up here and say, maybe write a line of code that says, if the length of the noise wave, not itself, but its shape, is greater than 1, or we can say equals 2. So if we have two dimensions, another way is to say if noise wave shape 0th dimension, which is the channel dimension by default, which is 2 right now. If it equals 2, then just pick one of them. So then the noise underscore wave would be its first channel. Then you can later check the shape again to see if everything worked smoothly. So I'm going to load the audio, check the shape. If the shape number of channels is 2, just get the first channel. You can display it. Sounds the same. You can resample it. Sounds the same. And now we can easily plot it now without having to index. So this is my noise wave file. The next step would naturally be to pad this to arbitrary dimensions, because we want to take window size of the audiobook, it could be 5 seconds or 10 seconds, and combine it with the noise. So we want to mix them down together into just one sample. We need both to have the same length. So right now my noise is too small in this case. There's only around 45,000 samples. So what I want to do, we want to pad this either on the left or right or both dimensions with 0. So let's see how padding works here. I'm going to use torch nn functional pad that we saw. So torch nn functional pad. Let's have a look at the arguments. So we need an input tensor. So for input tensor, I'm going to give it my noise wave. and it's going to take a tuple as a pad. So what this tuple essentially means, if you have multi-dimensional tensors, it's going to pad it on the final axis, on the last axis, by default. So if you want to pad this final axis, you want to either pad it on the left or right or both. So that's why it takes a tuple of even size, because the first value here would tell PyTorch how much you want to pad to the left. The second value will tell you how much you want to pad on the right. So on the final dimension, just as an example, I'm going to pad my noise by 0 values, by 0 amount on the left, by 1 amount on the right. Now I can choose the mode. I want to use constants. I want to change it. But I can pass the value now and say pad it with 11 just to see. So here you see on the left, no padding. On the right, pad it with 1 value, which is 11. And the shape should have 1 more value. So 97, 98. If you want to pad it on the left and right, let's say by 1000 on the left, 10 on the right. So we get 1000 11s on the left one and 10 11s on the right. You can check the shape. Now this should have 1010 more values than the original tensor. So you get the idea. This is pretty straightforward in this case, since we have one-dimensional tensors. Now I said I don't want any noise on the left. I don't want any padding on the left. I want padding on the right. By how much? Well, we will set this later because we will have different sets of window sizes. But let's assume my window size, the chunk of each audio clip, is around 4 seconds. So 4 times the metadata sample rate. Which is 96,000 samples. My original WAV file has less than that. So I can say window size minus torch.shave. Let me see. My window size minus the size of my noise. In this case would be 50,303. So I'll use this as the amount of padding here. I can separately put it to make the code more readable. Amount to pad is basically this much. And this is regardless of the window size. We can set it later. So torch functional pad. I'll call this output padded. So noise wave padded by amount to pad. I want to pad it with zeros. I will see later why zeros when we get to the normalization part. So for now, the max of my audio value is 1.12 and the minimum is -1. And if you have a look at your wave plot here, you get values bigger than 1 and less than -1. That's why the initial part is relatively loud. Now, most of the time you want to normalize your audio to have maximum amplitude of 1 and -1. To see how this sounds like, let's scale our audio a bit. So let's call it scale down, kind of reduce the amplitudes here. And by dividing padded by a factor of 2, let's say. So scale down, and let's take the minimum and maximum scale down. Min. Now the minimum becomes larger, the maximum becomes smaller, so the range will shrink. And now we can call audio to take a listen to this scaled down version. Rate is the same as before. So let me just do a quick comparison of the padded wave and the scaled down version. So now you see the padded is 4 seconds instead of 1 second because we padded that to, let's see, a window size of 4 seconds. So noise is now 4 seconds with trailing silence. This is without scaling, and this is with scaling. You can scale it even more, let's say by a factor of 4. The values become much smaller. Take another listen. Okay. So what is happening here? Let me plot my original padded audio, which is padded, and compare it to the scaled down. So bigger than 1, less than -1, this is the original audio. And now we scaled it to less than 0.3 and bigger than -0.3, so much narrower range. But when you play it back, you don't notice any difference. That's the scaled down, that's the original. Why? Basically, the amplitude shows the amplitude of air pressure, the amount of air pressure that's exerted on the ear. And the ear would not really notice any air pressure. It notices the changes in air pressure. So in this case, it doesn't notice this peak. If, let's do it for illustration. If I create a torch, let's say ones with, let's say 100,000 and call it sound. So that's my audio, sound.shape. And I play it back. So this is an audio file that looks like this. So plt plot. Let's plot the sound first. Every value is 1. There's no oscillation here. It's constant. You might expect the amplitude is high. You might expect a continuous loud noise. But let's take a listen to this audio. So play sound at, I'm going to specify a sample rate, but let's lay it out at sample rate of 48,000. If you listen, this is going to be empty. It doesn't have any sound because the sound actually is not the amplitude, is the changes in the pressure. So this will sound completely silent regardless of what the value or the amplitude is. On the other hand, this waveform has oscillations, and you notice only the oscillations and relative movements. So if you scale it down to 0 to 0.3, you don't really notice any difference in the loudness or amplitude because the relative changes or distances do not really change. The only way you can notice is if you change the relative distances of the waveform. Just to illustrate, let me do a bit of clipping on the audio. So if I plot the padded by clip the values between -0.4 and 0.5 this time. So instead of scaling everything uniformly down to this range, I will clip. And let me see how this looks like before we listen to it. You see these high amplitudes are now flat. Now, since we changed the relative positioning of the clip, if we listen to it, you see there's a kind of bit of a change. Let me clip it even more. So 0.3. So we have clipped even more. Let's see if we notice any more difference. So yes, a sound becomes a bit more dull. So that's what happens if you change the relationship or the relative frequencies or oscillations here. Now, that's basically how sound normalization works. If you go on Audacity, Adobe Audition, different sound processing software, when you do loudness normalization, they change the relative amplitudes, not the absolute value of the amplitudes. So we try these things out. Next thing we want to try is to shift the audio. Now, why would I shift this piece of audio? Well, the reason would be if I want to combine this audio with other sounds from the audiobook, I don't want it to always appear at a specific time, which here it is around 5,000 samples all the way to 40,000 samples and it dies out. Then the model will automatically always predict that there's a noise at this position, or if there's a spike in amplitude in these ranges, it's gonna detect as noisy. But in real life on the test set, on the actual distribution, if there's noise in different portions of the audio, the model will not be able to identify them. So I want to arbitrarily shift this anytime I want to load a noisy file. For that, we can use torch roll, which is a really handy method in PyTorch that would take an input tensor, a shift amount, and a dimension, and it would shift the values. So imagine we have this simple tensor 1, 2, all the way to 7, 8, and we roll it on the axis number 2. It will say, well, we shifted by an amount of 1. So 8 will go to the beginning and 1 will be shifted here. So 8, 1, 2, 3, 6, 7. So that's exactly what we want. So let's see. So let me get rid of these empty parts. I just want to say my padded audio is here. That's my padded audio. Now I want to roll it. I call the tensor rolled, and I do call it as a method on padded. I say roll padded for me, and it's going to ask for shifts and dims. How much to shift and on what dimension? Well, for the dims, I would just say this is one dimensional. Let's take a look at the shape. So I can say roll on dimension 0. The shift amount, let's try out something first. So in this case, let's shift it by 20,000 samples. So by 20,000 samples, the result should have the same shape as my padded, which it does, but it should look different if you plot it. So PLT plot, instead of starting at 5,000 until 40,000, it's going to start at 25,000 up to around 60,000. So it practically shifted that. What happens if we shifted more than the length of the audio? It's going to be rolled back to the beginning. So let's see. Let's say I want to shift it by 60,000. And I will plot this. So the start is much later, but it will spill over into the beginning. And let's take a listen and see if it makes sense, if there's any such noise in the real world. Because if you do that augmentation, sometimes you need to keep that in mind. Is my added noise or is my data augmentation really natural? Does it happen in real life or not? So this is how this rolled noise sound like. Yeah, so in the beginning you see the last part. Yeah. And then it starts a bit later. Seems fine for our use case. So what we effectively did, we padded our audio file into arbitrary length, which is our window size, and we made a function that would shift it and roll the audio as much as we want while maintaining the original audio's formation. Now, I don't want to each time tell my dataset how much to shift, how much to roll. So I want to create a random number that tells it to shift it by that amount. For this use case, I'm going to create a random uniform number generator. So in PyTorch, there are several ways you can do it. So I can first say, give me a torch 1. Let me call it random. It's not random right now. But let's call this random. It's going to give you just one tensor of 1. And then you can say random dot uniform underscore. It's going to in place take samples from a uniform distribution. Here you can set the start and end point. So in our case, we want it to be anything between 0 all the way to the size of the audio. 0 being no shift, and the end of the audio would be basically same amount of shift, would be 360 degrees, would be no shift. Anything in between would be some level of shift. So start would be from 0 all the way to the length of my noise, padded, so I would say padded shape 0. So if I run this, it's going to give me different uniform numbers between 0 and my padded shape. The issue right now is that these are floating point numbers, but I want to be able to index with these numbers into my audio array. So these should be integers or sample numbers. So I can basically cast it into, let's say, integer simply in PyTorch, and it's gonna return my number. So I'm gonna get it back. So now we get different integers. All right, so let's try it out on our audio file like a bunch of times. So if I take a random number and basically roll my data by that much, let me check how it looks like. So I would take the padded, roll it by this random amount on the 0th axis. Let's see if it works. It says shifts is required because right now my random is a tensor. To turn a tensor into a Python number, you will take the item attribute of it. So now it works. I can also display it with matplotlib, so plt plot, and see how this looks like. I might wanna maybe print the random value each time I run this. Okay, so let's see. So right now it's shifting by 15,000. That's how this looks like. Now 13. So when you're working with large ranges where the minimum and maximum are orders of magnitudes apart, you might want to display the distribution of your random numbers and see if it makes sense. In some cases, if you choose like a normally distributed value that will basically range between 0 to 100,000, it's going to favor small or big numbers all the time. So you might want to take the logarithm or square root, or maybe take it to the exponent. In this case, let's write a quick loop. So I'm going to create an empty list called numbers list, and I will go through, let's say, a range of 1,000, generate a random uniform number. So the same code, random uniform number in this particular range in the plot. And I'm going to just add the random number to my list. So num list append random as an integer, and let's plot it to see how it looks like. So plt plot num list. So right now plt plot might not be the best plot for this type of data. We want to look at the distribution of the data in this particular range, the frequency of each unique value. So you might want to try histogram, scatter plot. It depends on you. So like right now, it says 0 shift is almost as likely as a shift of 80,000. So in this case, this might be what we want. We want to have no shift at all in the noise, or be a bit here, a bit here, a bit here. Every position of the noise we want to be equiprobable. So in this case, we don't need to scale our uniform distribution. So right now, any amount of shift has equal probabilities. See? Now there we have it. So in terms of next steps, the next steps would be just to combine this prepare noise step to my large audio data set. So when I load the audiobook that I downloaded from LibriVox and take a window length of it,
converse of that young lady whose bright eyes are,
add a random noise, which could be at different portions of the segment, to it, combine them together. So in the next part, we'll see how to combine them, create a data set which is synthetic, and we basically can create infinite amount of data with just one sample noise here. And we already know the labels because we added the noise ourselves. Of course, a drawback to this would be our detector model can only detect this specific type of noise, not others. But that's a good starting point. So we can add other types of noise later as well. Or to make it more resilient, as we detect more noises, we can sample them later. But that's a good starting point to create an automatic data set. Thank you very much.